I'm Dr. Sean Humbert. So today we're at the Autonomous Vehicles Laboratory here at the University of Maryland in the A. James Clark School of Engineering, and we're very happy to host Olivia Smith-Donovan.
Hi, my name is Evan Ulrich. I'm a research graduate assistant here at the University of Maryland, and today I'll be talking to Olivia about bio-inspired flight design and how the different wing shapes take form and their effect on the flight dynamics, and how it relates to maple seeds and our robotic Samara, which is our version of a maple seed that we've been able to take off from the ground, hover, and perform flight. So we're going to go over some of the maple seed designs that we've come up with, and then we're going to let you design your own, and then we can test it out. All right, let's do it. So this is A41. We have B41, and you can see how it's a little bit different shape, right? Yep, that's a B, it looks like. And then we've got C41. It should be exactly that one, actually. D is this. It's a triangle.
That looks weird.
And you know what? This is the one that didn't work. It fell the fastest. In nature, generally there aren't any straight lines. Everything's curved, really. What we can do with our computer-assisted design is calculate where the weight is in the maple seed, and then where it needs to be. And what we've found is that it needs to be generally in this area here.
And then from here.
Yeah, and so that's why you see that this is thicker than the rest of it. So we can actually, balance it right here. So that's the center of mass right there. And so the whole seed then rotates around it like that. We would hoist these maple seeds up to the ceiling and then drop them, and then the system would track these little retroreflective markers on here. These cameras, they're surrounded by LEDs, which are little lights, and they flash at the same speed that the camera is taking pictures. That red light bounces off these retroreflective markers and then goes right back to the camera. So what you get is a video of just the markers falling in space. So this is slowed down quite a bit. This whole flight actually took about a second. You can see it passing by the cameras. And so that's a little glimpse of the flight path that it's taking. And it allows us to track them very, very accurately. Those 4 different designs that we just talked about, A41, B41, C41, and D41, these are the flight paths that we recorded. So we can see their performance down here. This is how fast it fell. Negative 1.8 meters per second is pretty fast compared to negative 1.5.
Got it.
Guess which one did the best? So the reason that we found out as to why it did the best is because this one has the most area farthest from the center of rotation. So they're the same size, but they're different shapes. So what we're going to do is we're going to start out the vehicle in a hover position.
Got it.
And you see how sensitive that control is? Look how much you're moving the wing. You just need to move it a little bit, just like that. Either the thing falls straight down, or it takes this large helical path down. And the difference between the way that it flies is the angle of the wing that you're saying. So if it's at a really high angle, like this, it's falling just about straight down. But if it's at a low angle, then it's carving out these large helical paths.
All right, now bring it down. Bring it up. There you go.
All right, Olivia, now that you've had a chance to fly around the robotic Samara, hopefully we can figure out how the wing design can affect the performance. Okay, so you just click on this point here, and you can drag it. So what you're doing here, by changing the geometry of the wing, is you're going to vary the speed at which it descends. So now this is the shape that you started with. Okay, that's what you want. We're gonna have your name on here. Check. Okay, we got there, Olivia. So we should be able to do some drop testing today of your newfound design, which
Great.
looks like it's gonna be an improvement, seeing as you have moved the center of area farther from center of rotation. So this should fall down slower than the other ones that we've got here. We can have a race to the bottom,
This and this?
and whoever gets to the bottom first loses. Right?
Yeah.
Okay. Right this way to the rapid prototyping machine. So what happens is this printer head moves across this surface here and builds up layer by layer your maple seed. So by the time this thing's done, where there is nothing, there will be Olivia's maple seed. Ready to see your cookies freshly done?
Sure.
All right, so looks like we've got a batch of 4 Olivia seeds here, hot off the press. So whoever gets to the bottom first loses. Okay, so this is a test between Olivia's seed, C21, and a D21. 1, 2, 3, go. So our theory is correct. Yours won by a long shot. So congratulations on that. You've clearly understood the flight dynamics of maple seeds quite well. I want to thank you for coming out and joining us today and congratulate you on winning the Kids Science Challenge. Thanks for coming out. It was good meeting you.